So recall last time we did derivatives of trigonometric and inverse trig. And in general, what I'm going to focusing on sine and cos and tan. Audio should be the same. I haven't set anything up any other way than I usually do. Let me check the volume. I'm on the computer in the office. My daughter uses it most of the time. And so if she changes settings, they just did an update to nobody comes to these anymore. As soon as they know that I'm going to post them every time, nobody shows up at 8 in the morning. We're the only suckers that have to. I will have to because I'm the teacher, but I don't know about the audio. I'll check it. As far as I know, it should be okay when I post it anyways. Or it's because I'm out of breath because I just ran here. I don't know. So in particular, the derivative specifically of sine x is cos x. The derivative of cos x is negative sine x. And in particular, these derivative rules so the derivative rules give us integral rules eventually when we first start doing integration, which will be next week after L'Hopital's rule. But the idea is all of these derivative rules are integration rules eventually. Secant squared x. So if you integrate all of these is what I'm saying. You get that these would cancel off. And then the derivative rules are integration rules eventually. We won't do that now because we're not going to do integration. That's immediately. So we should know that the integral of secant squared is tan. This will be a whole category that we're going to do. And then the other ones that are good for this are the derivatives of the inverse trigonometric functions. Give us an insight into how to do partially the trigonometric substitution when we get there, and partial fraction decomposition. Arc tangent will be extremely important. So the derivative of arc sine, or sine minus 1, equals 1 over the square root of 1 minus x squared. The derivative with respect to x of cos minus 1x equals negative 1 over the square root of 1 minus x squared. And the derivative of tan minus 1. Arc tangent is equal to the important one, 1 over 1 x squared. So a proper, rational, irreducible polynomial integral is arc tangent. This one is the important one. But these are the main 6 trigonometric ones that on exams I'll try to focus on. You don't have to worry so much about the other 6 functions and their derivatives. So that's what we did last time. This time what we're going to do is the last category of functions, which is the hyperbolic functions. Their inverses and the derivatives. also have class 11 to 12:30 and 12:30 to 2 today, so it's a big one on Thursdays. So what are the hyperbolic functions? The hyperbolic functions are linear combinations of exponential functions. So let's give a story. I'll give the first story of where we get the definition essentially from, and then where we get the terminology from, we can do at the end. But what I'm going to do first is we're going to discuss even and odd functions, and then I'll give a result about even and odd functions. You're like, why are you talking so much about even odd functions? It's like one of the steps we did when we did curve sketching in 114. Step 3 is find symmetry in the Stewart calculus book. It says there's 2 types of symmetry, even and odd functions and neither functions, and then periodic functions. And you want to find symmetry to save sketching time. If you're even, you're symmetric with respect to the y-axis. If you're odd, you're symmetric with respect to the origin, which means you reflect about this axis, and then the x-axis, both axes is the origin. And so what are they talking about? Basically, long story short, I'll even give the punchline now. Sine hyperbolic and cos hyperbolic are the even and odd part of e to the x. What? So I'm going to go through that now. Remember definition. Function, let f be a function. With 0 in the interior of its domain. All we mean there is to be able to take negative x, we have to have 0 in the interval so we can go x and negative x. If 0 is not in there, then we can't go across it. It makes no sense. So 1 f of x is called even if we have that f of negative x equals f of x. So it spits out this, and then we have symmetry. 2 f of x is called odd if we have odd functions of the polemics. They spit out the negative. So if f of negative x is equal to negative f of x, 3 f is neither even nor odd. If both of these are negated, negative f of x doesn't equal f of x, and f of negative x doesn't equal negative f of x. So why do I want this? Basically, why do they call them? Why do we have this terminology, even and odd? Sine and cosine are odd, so decide if each function is even or odd. Or neither. So this is a trichotomy too also. This splits the category of functions into 3 categories, not 2. Your even function, your odd function, or your neither. And what that means is either you're symmetric with respect to the y-axis, you're symmetric with respect to the origin, or you don't have symmetry with respect to the axes. So if f of x is equal to cos x plus the absolute value of x plus x squared plus 1. Or if you want neither, f of x is equal to, let's say, x to the 4 plus x cubed. That's good enough. So even, odd, neither. Why? Solution. What you have to check is you have to check every time whether we're sketching. We will do curve sketching a little bit in here again, I think. Transcendental functions. We have to check what happens to negative x when we put it in a function. So in this case, I get cos of negative x plus the absolute value of negative x plus negative x squared plus 1. cos x is even, so it eats the x. Absolute value is even, so it eats the negative. Absolute value of negative x equals absolute value of x. And x squared kills the negative. And so this is equal to f of x. So this function is even, whatever it looks like. We have an even function. In the second case, f of negative x is equal to sine of negative x minus negative x cubed plus negative x. This time I can spit a negative out in each one. This is negative sine x. This is negative x cubed. And then minus x. I have a negative in each spot, each term, so I'm going to factor negative out. Negative sine x minus x cubed plus x. That's f of x. So we get an odd function. And then when we have a mixture of these, f of negative x, if we have mixed power of even exponents and odd exponents, this will be neither. This is negative x to the 4 plus negative x cubed. This first term, x to the 4, kills the negative, but now x cubed spits it out. This does not equal f of x. This does not equal negative f of x. If you look at them, f of x is x to the 4 plus x cubed, two positive terms. Negative f of x is equal to negative x to the 4 negative x cubed. But our function has one positive and one negative term. F of x needs two positive terms. Negative f of x needs two negative terms. But our function with f of negative x, so this has neither, no symmetry. This is neither even nor odd. Right. Why do I want this? Well, now I want a theorem which is going to say magically, if you have functions like this, even if it isn't even and odd, you can write it as an even part and an odd part. That's, in this case, x to the 4 is the even part of this function, and x cubed is the odd part of the function. But I can do it for every function. Theorem. Let f be a function with 0 in its interior. Then f of x can be written as the linear combination of an even and odd function. I.e. f of x equals f odd plus f even, where f odd of x is equal to 1/2 f of x minus f of negative x, and f even is 1/2 f of x plus f of negative x. This is the odd part. So I don't know what you're asking. Yes, it does spit out a negative. It did spit it out right there. Yeah, but there's already a negative there for part 2. I still have one negative. That's why I wrote it like that. I have one negative, one negative, one negative, and then I pulled it out. That's where I pulled it out. But I still have a negative left. This is where I'll get you. I don't need to even use fancy functions. I'm going to get everybody with negative on exams because everyone hates it. 2 negatives make a positive. But if I have 2 negatives, I can take one out. Yeah, I'll get you with negatives. That's why I put the negative in the function. Because you have to put negative in the function by definition. Right here. And now I'm putting negative x into there. So there's going to be 2 negatives. I'm only taking one of them out. So one of them stays. But I still get my function back. Up to the negative. And now with the theorem, I'll prove the first part. You can show that these are even and odd functions. But the reason I show the proof is because I try to convince everybody my 2 dirty tricks are I multiply by 1 and I add 0. I'm going to use both tricks here. So what do I write? I start with f of x. I want to show f of x is something fancy. Here's where I get literally something for nothing. I write this as 2 over 2 f of x because 2 over 2 is 1 and multiplying f by 1 doesn't change anything. Now what I do is the 2 on the top, I write it like this. 2 f of x is f of x plus f of x. That was clever too. All I did was say, well, 2 of them is f of x plus f of x. I'm trying to create these even and odd functions. So now what do I do? On the top, this equals f of x plus f of x. I need f of negative x, and then I'm going to subtract it. This is 0. This is 1. So now I've added 0, which doesn't change anything. But now what do I get? I regroup this. This is f of x minus f of negative x over 2 plus f of x plus f of negative x over 2. And that's just my fo of x plus fe of x. And you can show that fo is odd and fe is even. You just put negative x in there and show that you get the same thing. So why are we doing this? What's the big deal here? Well, example. Let f of x be e to the x. Then fo of x is said to be 1/2 e to the x minus e to the negative x. And fe of x is 1/2 e to the x plus e to the negative x. This says e to the x is equal to 1/2 e to the x minus e to the negative x plus 1/2 e to the x plus e to the negative x, or e to the x is equal to sine hyperbolic x plus cos hyperbolic x. Cos hyperbolic and sine hyperbolic are the even and odd part of e to the x respectively. This is where they're coming from. The hyperbolic term comes from where we traverse on the unit circle versus the unit hyperbola. I'll get there in a second. So definition, most books will just start with this and just throw it at you. Hyperbolic sine and cosine functions. Are defined as sine hyperbolic x is just 1/2 e to the x minus e to the negative x, and cos hyperbolic x is equal to 1/2 e to the x plus e to the negative x. Also from this, then tan hyperbolic x is equal to sine hyperbolic x over cos hyperbolic x, which is going to be e to the x minus e to the negative x over e to the x plus e to the negative x. The other ones are going to be cosecant hyperbolic x is going to be equal to 1 over sine, which is 2 over e to the x minus e to the negative x. Secant hyperbolic x is going to be 1 over cos hyperbolic x. This is the reciprocals as usual that we see. This will be 2 over e to the x plus e to the negative x. And then cotangent hyperbolic x is equal to 1 over tan hyperbolic x, which is cos hyperbolic x over sine hyperbolic x, which is equal to e to the x plus e to the negative x over e to the x minus e to the negative x. These are the functions. The three main ones, their graphs are going to be awfully similar to x cubed, x squared, and then our hyperbolic, tan hyperbolic is slightly different, but sine hyperbolic is the odd one. Cos hyperbolic looks like the parabola, but it's shifted up. And then show how to do this in a little bit when we get back to limits. This is 1 and this is minus 1. This is tan hyperbolic x. So notice tan hyperbolic is bounded. Absolute value is less than 1, which means it's stuck between minus 1 and 1. It has horizontal asymptotes of positive 1 in the positive direction, and it has a horizontal asymptote of negative 1 in the negative direction. I'll get to how we calculate these things when we start talking about limits, etc. Maybe I should do that now. But the other thing we want to do is Pythagorean identities and get to where we get the term hyperbolic from. Just a second, I have to go stop it. Sorry, I don't know if you can hear in the background because it dulls the background noises, but there was cat fight, and it's not a cat fight. They're bored, they went outside. So this is sine hyperbolic, cos hyperbolic, tan hyperbolic. In particular, when we're doing limits, and we want to discuss the horizontal asymptotes of tan hyperbolic. We get these new functions. You need to know the new dirty tricks that we're going to do for limits at infinity. So I'll go over that again. The dirty trick when you do this for limits at infinity for polynomials, and then now what do we do for these transcendental functions? So let's talk about, say I have f of x, which is x cubed plus x plus 1 over 2x cubed plus x squared. This limit is 1/2. I can tell immediately. How are we going to do this? We're going to do the dirty tricks that hopefully you were trained in 114. If you didn't get this, then I'll do it now. But there's tricks at infinity. When I'm going to infinity, when I'm pushing to positive or negative infinity, either I factor out the highest power on the top of the bottom, or if I have a radical, I conjugate a lot of the time to simplify. Those are the two dirty tricks. Versus now we have a new type of function, g of x, which is tan hyperbolic, which is e to the x minus e to the negative x over e to the x plus e to the negative x. What are we going to do? So for the first one, if I want to I'll look at the limit as x approaches infinity, positive infinity, of x cubed plus x plus 1 over 2x cubed plus x squared. And this is going to equal, you have to write it out every time, the limit as x approaches infinity of x cubed 1 plus 1 over x squared plus 1 over x cubed. So I'm factoring out the x cubed out of the top and the bottom. And then I should have x cubed here. I should have 2 plus 1 over x. Those will now cancel after I pull out the highest power on the top and the bottom. How I'm really doing that is I'm writing x cubed over x cubed, x squared over x squared. I'm doing the same thing. I'm multiplying by my dirty trick. Squeezing it in there. Now I can factor out x cubed out of each one. What does that give me? This gives me the limit as x approaches infinity of 1 plus 1 over x squared plus 1 over x cubed over 2 plus 1 over x. Why did we do that? Because we have to know from our lexicon all of these reciprocal Atari functions, all of them go to 0 at infinity. That's why we do that. We're going to have to do the same thing for the transcendental function, but now you forget. So what does this equal? This just gives me 1 plus 0 over 2 plus 0, which is 1/2, like I promised. It should be if the degree of the top and the bottom are the same, this is improper rational function. And therefore, if they're equal, the degrees, the limit will be the leading coefficient over leading coefficient, so 1 over 2. How do I do this for the new transcendental function? And the reason I knew this was because we know that all of these Atari functions, whether it's 1 over x or 1 over x squared or 1 over x cubed, we know that all of these limits, that's the limit as x approaches infinity of 1 over x squared equals positive infinity, is what that's telling me. We already know this. So now when I go to switch to the new function, g of x equals tan hyperbolic x, which is e to the x minus e to the negative x over e to the x plus e to the negative x. How am I going to take these limits at infinity? What I want to see now is this. If a is a positive number, then e to the ax does that. And if a is a positive number, e to the negative ax does this. I don't care what the value looks like, or it doesn't matter what the base is. It can be any base as well. But what is that telling us? This says you should already know this. If you don't, start paying attention. These are the ones you want to memorize for the new transcendental functions. This tells me a limit. If you're not picturing the behavior of a function near a value or at infinities, you're doing limits wrong. What does that say algebraically? This says the limit as x approaches negative infinity of e to the ax is equal to 0. So if I go in the negative infinity direction, I want to keep positive a's to the x's, is what it's saying, because I can make them all go to 0. If I have, what does this say? This says the limit as x approaches positive infinity of e to the negative ax is also 0. I want to use these two things to compute my limits now. But instead of multiplying the top and the bottom by the highest power of x, we're going to multiply by, see, the other thing we could do here is, instead of doing this, what we're doing is we're multiplying by x to the negative 3 over x to the negative 3. So I look, I say, what's the highest power? X to the 3, so I can multiply by x to the negative 3 and get rid of them all. I multiply by 1. Now what am I going to do? I'm going to mimic the same trick, but instead of the polynomials, I have the limit as x approaches, say, positive infinity of e to the x minus e to the negative x over e to the x plus e to the negative x. And I say, which do I want to keep first of all? I'm going to positive infinity. So I want this case. When I do that, I want to keep negative e to the negative ax goes to 0, so I can make those go away. So I want to keep the negative e to the x, and I want to get rid of the e to the positive x. So the way to do that is I multiply by the top and the bottom by the largest power of e to the x. I want to multiply by the opposite. So here I'm going to multiply by e to the negative x over e to the negative x. Why? Because it will get rid of the positive e's. Now distribute that in there. This will give me the limit as x approaches positive infinity of 1 minus e to the negative 2x over 1 plus e to the negative 2x. I just distributed it and use exponent laws. Now I see that this is going to go to 0 and this is going to go to 0, just like I wanted for the polynomial one or the rational function. And then this tells me I get 1 over 1, which is 1. Therefore, the horizontal asymptote of y equals 1 in the positive direction, which we knew already, but when I drew it, this is what we just described. So the horizontal asymptote of 1, you need to know how to do this algebraically. So what's the dirty trick? The dirty trick is now that you have these new transcendental functions, hyperbolic functions, I deal with limits the same way I deal with limits at infinity for rational functions, except you have to multiply by, instead of the highest power of x to the negative 3 over x to the negative 3 to cancel the x cubed. I have to cancel, I have to say when I'm going to positive infinity, I have to multiply by e to the negative x. If I go to the other direction, the limit as x approaches negative infinity of e to the x minus e to the negative x over e to the x plus e to the negative x. Now I look at this and I say, oh, when I go to negative infinity, I want to keep positive a to the x as e to the ax because they're going to go to 0. So I multiply, I want to get rid of the e to the negative x this time. This time I'm going to multiply by e to the x over e to the x. In the form of 1. Now when I distribute that through, I get the limit as x approaches negative infinity of e to the 2x minus 1 over e to the 2x plus 1. And now these are going to go to 0. And then that's going to give me 0 minus 1 over 0 plus 1, which is negative 1. There's a horizontal asymptote. Y equals negative 1 in the negative direction. So that's exactly what we had from the picture originally. There's a different horizontal asymptote in the negative direction. You always have to check both. So horizontal asymptotes, you can have at most 2 horizontal asymptotes. In this case, we have exactly 2 for tan hyperbolic, and he's bounded between minus 1 and 1. Y equals tan hyperbolic x is bounded. The other ones you have are arc tan is bounded by negative pi over 2 to pi over 2, and sine and cosine are bounded by negative 1 and 1 also. Also, why the terminology hyperbolic? Where is this terminology coming from? Anybody know? It's not sinh and cosh, which you're going to say anyways, but it's sine hyperbolic, cos hyperbolic. I don't think people get this because I should do the crash course in trigonometry as well. So for the trigonometric, how do we actually define these? Sine and cosine are originally defined by doing this. You get a circle of radius 1. We start at the point right here, which is 1, 0. After we travel a distance t on here, we stop at a terminal point t. Because of that, this is also the inner angle is the length of the curve subtending that angle. This is how we measure angles. So this is t in both cases. This is where we link the trigonometry of right triangles to the trigonometry of real numbers. Now what that says is this point here, P, says that our x coordinate is cos t and our y coordinate is sine t from the trigonometry of right triangles. If we actually look at this, this is a 1, and then we get the definition of sine and cosine. Opposite over adjacent. This is what we get. So on the unit circle, this is the unit circle. And its formula is x squared plus y squared equals 1. And then that says that cos squared t plus sine squared t has to equal 1. This is our first Pythagorean identity. Where do you think it comes from? Pythagoras' theorem. This is just Pythagoras in a right triangle. So why are they calling it hyperbolic? What they did was Einstein notices that this is the hyperbola. And its equation is x squared minus y squared equals 1. So for any angle t, we have that cos hyperbolic squared t minus sine hyperbolic squared t is equals 1. That should be true because it's on the hyperbola. These are points on the hyperbola. They must satisfy the hyperbola's equation. These are points on a circle. They must satisfy the circle's equation. So what is this? Cos hyperbolic squared x minus sine hyperbolic squared x is equal to 1. This is the Pythagorean identity. It's like, why is there a minus? Because we're on the hyperbola, not the parabola anymore. So after I start at this point 1, 0, and I travel a distance t on here. Cat's fighting again. I'm going to ignore it. We're almost done. Where do we end up? We ended up a point, and this will be cos hyperbolic t and sine hyperbolic t. So after you travel a distance t on the hyperbola instead of the unit circle, we end up at the points cos hyperbolic, sine hyperbolic. And this is where we get the terminology hyperbolic functions, because we're mimicking the definition of how to define these things on a hyperbola instead of on the unit circle like the trigonometric functions. So some of the identities will be the same. Some of them won't be. There's a negative, you have to keep track. But this is where we get the terminology hyperbolic from, and where the hyperbolic functions come from is essentially the even and odd part of e to the x. And Einstein is using these in general relativity, and he's sick of calling them 1/2 e to the x plus minus e to the negative x and 1/2 e to the x plus e to the. So he's like, I'm going to call these sine hyperbolic and cos hyperbolic. So this is where we get the terminology from. Einstein, that dude. Thank you, Einstein, I guess. But this is where we get the terminology hyperbolic. What else did I forget? So identities. Most of these are derivable because when you get stuck with hyperbolic functions, just turn it into the e to the x, especially taking derivatives. It's the easiest derivative to take. E is its own derivative. But what do we have? First of all, we know that e to the x is sine hyperbolic x plus cos hyperbolic x. This is by definition of those. 2, we know that now cos hyperbolic squared x minus sine hyperbolic squared x equals 1 for any x, because it's on the hyperbola. And the hyperbola's equation is x squared minus y squared equals 1. That's where the minus comes from. 3, I won't list too many of these, even and odd. So sine hyperbolic is odd. 4, it is the odd part of e to the x, so it better be odd. And cos hyperbolic of negative x better be even, because it was the even part of e to the x. 5, we're going to have the addition formulas. Sine hyperbolic x plus y is equal to sine hyperbolic x cos hyperbolic y plus sine hyperbolic y cos hyperbolic x, and then cos hyperbolic x plus y cos hyperbolic x cos hyperbolic y plus, there's no minus, sine hyperbolic x sine hyperbolic. In my lecture notes, I do the other identities, but the other ones will be the double angle identities. Sine hyperbolic 2x equals 2 sine hyperbolic x cos hyperbolic x. And cos hyperbolic 2x is going to equal plus. So those are the major identities similar to the trigonometric identities. Let's begin versus. I'm going to focus on sine hyperbolic, cos hyperbolic. Tan hyperbolic, how much time do I have left? Like 5 minutes. We get nice formulas. So as you can see from the 3 functions, where did they go? Here we go. They're not 1 to, cos hyperbolic isn't 1 to 1. He fails this horizontal line test. So just like x squared, we're going to restrict him, or the sine and cosine functions. So he's the one we'll restrict. But for the other ones, sine hyperbolic is the one where you really don't have to pay attention. So for the first one, we know that sine hyperbolic is going from R to R. Therefore, sine hyperbolic inverse is also going to go from R to R. What is that going to give us? That's going to give us, if this is sine hyperbolic, then this is sine hyperbolic inverse of x. And then yes, just as usual, sine hyperbolic, following sine, all the cancellation rules exist and everything like this again. But this is the main picture. This is the nicest one there is because there's no restrictions. So you can go from R to R. The cancellation happens everywhere. In general, no, we don't give any information on quizzes or exams. they're expecting you memorize all of them, they being me. In most cases, you won't need them, but they're just awfully similar to the trigonometric ones. But again, when this looks like a shell shock of new functions, remember that they're just the even and odd part of e to the x. So they're just linear combinations of e. All you really have to know is remember the definition, and that should get you out of most cases. All right. Or 2, cos hyperbolic is going from where? 0 infinity into 1 infinity. So cos hyperbolic inverse is going to go from 1 infinity into 0 infinity. They swap their domains. What do we mean by that? This was 0 to infinity. This was cos hyperbolic x 1 to 1. So what we're going to get is this guy. It's going to look like root x just shifted over, just like when we have the regular parabola and root x. It's the same business. And then finally, the third one, we have tan hyperbolic x. Where does it go from? It goes from r into -1 of 1. So tan hyperbolic inverse has to go from -1 to 1 into all the real numbers. What's that going to look like? This will look like what we're going to get if arctan looks like this. So this is tan hyperbolic x. This is tan hyperbolic inverse of x. So they do look awfully similar to the polynomials and trigonometric functions, but these are the hyperbolic functions. And their inverses. Now what do we have? The inverses we can actually write for the hyperbolic functions. Because we're writing these now, we have this new function e to the x, and its inverse log x. So we now know that e to the x and natural log x cancel each other when they touch. And then we're making sine hyperbolic and cos hyperbolic from algebraic combinations of e's with plus and minus and division. So we can explicitly solve for, using the logarithm, we can find an explicit formula for these. And that's what I'll do next week, I guess, starting off, is give explicit formulas. For hyperbolic. So we'll do that next time. But we have a nice formula. What we mean by that is sine hyperbolic minus 1, for instance, is equal to the natural log. I never memorized x plus the square root of x squared plus 1. Like, how are they getting these? I'll show you next time. Have a good weekend. I'll see you. I'll post this later today. I have to get it to, once I do this, it has to download onto here. And then when I upload it, I have 2 more classes today. So it'll be later today by the time I remember. Have a good weekend. I'll see you